Alright, so this is the first video in my series on applied physics. We're going to start off looking at some rotational motion and looking at comparing the equations we already know from linear motion and looking at how similar they are to the equations of rotational motion and the fact that we'll use them in very similar ways. Let's quickly start off with some notation and definition so you know what I'm talking about later on. So for every linear thing you know, there's going to be an angular equivalent. So in linear motion, we have displacement. So that's the distance in a certain direction. When you're dealing with rotational motion, you have angular displacement, and it's measured in radians. You also have angular velocity, which is the rate of change of your angular displacement. So it's the number of radians per second. Just occasionally you might see it given this symbol over here, so I've included this column on the right hand side of the table so you don't get confused. There's slightly different notation for different things depending on where you're reading about things, so watch out for that. You also have all these other properties, so you've got your angular acceleration, you've got torque, which is the rotational equivalent of a force, you've got angular momentum, and those of you who are interested in like particle physics and looking at atomic structure, you might recognize the symbol L from somewhere else. You also have rotational kinetic energy, and you have this property called moment of inertia, which I'll talk a little bit more about later on. Okay, so those are the key symbols and their units and that kind of thing, so make sure you have got a note of what those are. Then in terms of some key definitions for dealing with this topic, so mass we've encountered already. So it's an object's resistance to linear acceleration. So that's where Newton's second law, F equals ma, comes from. M is essentially how much the object doesn't want to accelerate. So the larger the mass, the more force it takes to get the same acceleration. And there's an equivalent in rotational motion. It's called moment of inertia, or sometimes inertia for short. So that's an object's resistance to angular acceleration, and it depends on the mass as well, but there's other factors which affect it, so it's not just the mass, it's where the mass is that's also important. But again, we'll get to the equations and stuff like that later on. And a torque is essentially the equivalent of a force in rotational motion, but essentially instead of just causing it to move in a linear or a straight line, a torque is causing something to rotate, and it causes it to rotate about a fixed point or a fixed axis. So those are the key definitions and properties and that kind of thing. So let's move on to dig a little deeper into this. So as I said before, essentially for each linear equation there is an angular equivalent. So we're going to go through what those are. So in linear motion we have F equals ma, so the resultant force is the mass times acceleration. Well, in rotational motion you have similar equations, so the resultant torque is the moment of inertia times by the angular acceleration. So it's very much of a similar form. And the momentum, very similar. So whereas in linear motion it was mass times velocity, here is going to be the moment of inertia, which is the angular equivalent of mass, times by the angular velocity instead of the tangential velocity. To get the rotational kinetic energy, we're following a similar pattern here. So anytime you see mass, you replace it with moment of inertia. Anytime you see v, you replace it with omega, or angular velocity. So you have this. So to calculate the angular work done, it's going to be the torque times by the angular displacement. And to get the power in the angular direction, is going to be the torque times by the angular velocity at that given point. So you can calculate what the power is at that point. So those are your general equations. There's also angular equivalents of Suvat equations, so let's take a look at those. So here we've got v equals u plus at. So we don't have separate, in angular acceleration we don't have separate symbols for initial and final, so you will often see them with small subscripts. So the final angular speed is going to be the initial angular speed plus the angular acceleration times by the time over which that acceleration occurs. Hopefully fairly simple to follow and understand with that one. Then if we look at the increment, so the angular displacement is going to be the initial angular speed times time plus half of the angular acceleration times time squared. And then to get the final angular speed squared, we have the initial speed squared plus 2 times the angular acceleration times by the angular displacement. And then finally, if you want to calculate the angular displacement, we can do this very similar equation here. 2, and again you times that by t. So we've still got the same time as we had in all this. Time doesn't change if it's angular or rotational, but all the other properties have their own angular equivalent, and these are available to you and easily found in your formula sheet. So in some of the equations earlier, we've already had this thing called moment of inertia cropping up. So it's time to start thinking about what the moment of inertia actually is. So we've got this the resistance to angular acceleration, but how do we actually calculate what it is? Well, as a general rule, you calculate the moment of inertia as the sum of the mass times the distance from the rotational axis squared there. Or you very often see this in its integral form of the mass times the distance dr. So when we model an object as a series of tiny objects, we actually end up doing an integral there. And both these are expressing the same thing. So what are these equations telling you? Well, first thing it tells you is the more mass an object has, the more inertia it has. Okay, so that seems fairly sensible. But it also tells you that depending on where the mass is important for it as well. So if your mass is located further away from the point you're rotating about, that means you have a bigger r, which means you have a bigger moment of inertia. Or conversely, if you locate your mass close to the axis of rotation, that has a small moment of inertia. So for things like a wheel, if you want to be able to accelerate that wheel very quickly, therefore you want a very low moment of inertia, you're going to want to concentrate the mass towards the center of that wheel. And very often with wheels, you'll see they pack as much of the mass into the center, and then it actually tapers off. It gets thinner and thinner the further away it gets, trying to minimize the moment of inertia. Okay, so that's those. So let's have a look at some example questions so we can see these in action. So I'll show you some using the equations, and then I'll show you a couple of examples calculating the moment of inertia of an object so you can see how it works. Okay, so we have a turntable in a microwave oven. The examiners love microwave ovens. It's a very commonly known example of rotational motion. So we've got a moment of inertia there, then given a value, and it's got a vertical axis of rotation. So when you think of a microwave, it's rotating in the horizontal plane essentially. So we've got the initial angular speed of 6.4. It makes 8.3 revolutions before going to rest. So this is a very common thing to see. So the first thing we need to do is actually calculate what the angular displacement is. Because we've got the number of rotations, but we need to convert that into radians. So we need to multiply it by 2 pi, essentially, because that turns it into radians. So that comes out as it's around about 52 radians, but obviously we're not going to round at this point, but it's a useful thing to check later on. So then we're going to need to think about what equation we're going to use. So in this case, we're going to want this equation here, because we haven't been told anything about the time. So we're essentially trying to find this here. So let's rearrange it in algebraic form first of all. Ooh, I messed up my squared there. That was very clumsy. So we know the final speed is 0 because it comes to rest. So we essentially end up with minus 6.4 squared on the top line over 2 times 8.3 times by 2 pi. And if we put all those numbers in, we should end up with minus 0.39 radians seconds to the minus 2, which is your unit there. So key thing, it's decelerating where it has negative acceleration, so we'd expect to be seeing the minus sign there, which is good. And we've got two significant figures here, we've got 2 here and 2 here, so that makes sense as well. And we've got our unit radians seconds to the minus 2, so we've got all the things like the checks we can do to make sure we've got that correct. So what we've calculated here is the acceleration. So we need to calculate essentially the frictional torque that's acting on it. So if it's got an acceleration, that must mean a force is acting on it. So in our rotational motion, we know we've got this equation here. We've just calculated what the acceleration is. You're given in the question what I is, so we can got all the information we need to do a calculation here. And then times by 0.39 using our unrounded version. Blah, 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 blah. That is meant to be a 9. And if you put those in, you should get a number of 3.2 times 10 to the minus 3 Newton meters, which is the unit of your torque, because it's a force times distance is acting. We've got two significant figures here. We've got two significant figures here, so that's good. We've got our unit, and we've got a reasonable power of 10, because we had 10 to the minus 3 before, so we still got 10 to the minus 3. Makes sense. Okay, so let's move on. So we're now connecting it up to some sort of drive, and it's going to place a pi on the center of the turntable. We're putting a power of 900 watts in. Power is applied for 270 seconds, and it reaches its operating speed almost immediately, and we've still got the same frictional torque. So calculate the work done to keep the turntable rotating for 270 seconds at a constant angular speed of this. Okay, so first thing we're going to need to do, get our equation in rotational motion. So the power is going to be the torque times by the angular speed. We know what torque is because we just calculated it in the previous question. It was this 3.2 times 10 to the minus 3, obviously using our unrounded version. Multiply it by our angular speed. If we do that, we'll get our power, and then if we times that by the time, we will, because remember power times time equals the energy, we'll end up with our energy, and if we put those numbers in, we'll come up with 0.67 joules. To our checks, got units of energy, cool, got 2 sig figs there. We were using numbers that were 2 sig figs, that all works. It all seems to check out. So if we go on to the last part, so we need the ratio of energy supplied over the work done. So the first thing we need to work out is the energy supplied, which would be the power times by the time. It's going to be 900 watts times by 270. So then that's going to come out So then in terms of calculating the ratio, you've got a number which is 10 to the 5 over a number which is 10 to the 0 because it's not multiplied by 10. So that gives you a number that's approximately 10 to the 5, just looking at the powers there. Or if you actually calculate what it is, you should come out with a number that's 3.6 times 10 to the 5, which again is roughly 10 to the 5. Either way is absolutely fine, but you're showing it's about 10 to the 5. Okay, so let's look at some moment of inertia calculations. Okay, so first of all we want to calculate the moment of inertia of a rod with an axis through its centre. So let's draw a diagram. It's always the best way to start. What we say is we've got a rod of length L, mass is going to be M, and to start with we're doing it about its centre. So what we're going to do is we're going to ignore the other dimensions, so we're going to consider it being thin and it not having any depth, so these other dimensions don't matter at all. And what we're going to do is we're going to consider a small mass, length delta r, and this delta r will have a certain distance from the centre of rotation. So if we remember our equation, to get the moment of inertia, we need to integrate the mass in this form here. So what we need to do is actually express the mass of this small section in terms of a fraction of the whole length. So how are we going to do that? Well, to get the mass of this small section, mass of the little section, the total mass divided by the length. So this gives you the like the mass per unit length, and then you multiply it by the length, which would tell you the mass of this little length. So what we've done here is we've got the total mass divided by the total length, so that tells you the mass per unit length, and you multiply it by the unit length, and you can put this into your equation. So so we then have this expression here, so it's got the values that we need, and if that's length L, that must be L over 2 at this end, and this must be minus L over 2 at that end. So those will be the limits for our integral. So we put those in. Let's take the M over L outside, and we're going to end up with it's going up to r cubed, which means we'll take 3. And when you multiply those out and gather the terms, you end up with ml squared over 12. And this is the moment of inertia. So what we can see from this is the bigger the mass, the greater the moment of inertia. We can see that the greater the length, the greater the moment of inertia, and actually that's squared, so the length is actually more important in the moment of inertia. So let's see how this changes if we instead look about rotating it about one of the ends. So we're looking about the point of rotation here, but otherwise it's the same. So we've still got the same integration, so we've got a mass per length like this, except this time we've got L here, and then this distance is 0, so we're actually integrating it between L and 0 on this time. And 0. So that's going to come out as ml squared over 3. So you can see the point we choose to rotate about is actually important in terms of the moment of inertia as well. So you can see we've ended up with a number 4 times as big by moving the point about which we're rotating it. So that's another sort of point of interest there.